So for a turbulent flow over an isothermal plate, the best way to estimate the convective heat transfer coefficient for this turbulent boundary layer for isothermal plate, we use the fluid friction analogy. Or Colburn analogy. Recall that for Colburn analogy, what we had was a number called a Stanton number, local standard number, Prandtl to the power of 2/3 is CFX divided by 2. CFX is the friction factor. And the beauty of using this analogy is that it allows us to use a lot of experimental data available for friction factor. So we have a lot of data for this friction factor for different systems, and we can use them to evaluate Stanton number, and from there we can get the local heat transfer coefficient. So for isothermal turbulent boundary layer, the thickness of turbulent boundary layer, it can be estimated by 0.37x local Reynolds number to the power of -1/5. So this is the thickness of turbulent boundary layer, and CFX is going to be 0.0592 Reynolds number x to the power of 1/5. So we have a relationship based on the Reynolds number, and this Reynolds number of x is going to be, should be smaller than 10 to power 8. So this is the limitations, greater than the Reynolds number of x, and critical. And this critical Reynolds number for the transition from the laminar to turbulent for the flat plate depends on the condition, but we are going to use, and the widely accepted is 5 times 10 to power 5 for this flat plate. So that's the number that we are going to use. Now, starting from the Colburn correlation, Stanton number local 1 times Prandtl to the power of 2/3, which is the Nusselt number x divided by Prandtl number, Reynolds number of x, Prandtl number 2/3. It's going to be CFX divided by 2. And CFX divided by 2, if I replace it here, it's going to be 0.0296. Reynolds number of local -1/5. So if I do the rearrangement here, the local Nusselt number for a turbulent boundary layer in isothermal plate is going to be 0.0296 Reynolds number to the power of 4/5, Prandtl number to the power of 1/3. So that's the local one. So this is used for a turbulent boundary layer. It should be isothermal plate. Plate remains at a constant temperature, Prandtl number less than 50, greater than 0.6, and Reynolds number 10 to power of 8, greater than 5 times 10 to power of 5. And if we do the averaging of the local heat transfer coefficient, HL, and then do the evaluation of Nusselt number, the Nusselt number of average over the length of the plate is going to be 0.037, Reynolds number L 4 to 5, Prandtl 1/3. Similarly, if you evaluate the average of friction factor over the plate, is going to be 0.074, Reynolds number of L to the power of -1/5.